Hello everyone. So today we are going to be learning about finding global maximum and minimum of a function of two variables. Alright, so in contrast to last class when we learned how to use the second derivative test to identify critical points that were local maximum, local minimum, or saddle points of a function of two variables, today we are going to talk about global maximum and global minimum. Right, so there's a few terms that we'd like to define before we start with talking about how to find global max and global min of a function of two variables. And the first one is, given a region R in the xy plane, we call the region closed if it includes all of its boundary points. All right, so this all is very important. So it needs to include all of its boundary points. And a region is going to be open if it does not include any of its boundary points. All right, so closed means it includes all of its boundary points, and open means it does not include any of its boundary points. All right, so with that in mind, let's look at the following example. So first what we're given this region R1, right? So it consists of all points x and y, where the x coordinate here is between 1 and 5, and the y coordinate is also between 1 and 5. In both cases here, the endpoints are included. All right, so we're going to try to do that. So let's see what that means. So remember, x is between 1 and 5, boundary points are included. Included means we draw it with a solid line here. So we know x is between 1 and 5. And similarly, y is between 1 and 5 as well. Again, boundary points included. So the region in question here is that region there. All right, so the region in question is this region right here. So the question we'd like to answer now is whether that's closed, open, or neither. So what we would like to do is we would like to figure out whether it includes all of its boundary points, does not include any of its boundary points. So if we think about it, if we're looking at this region right here, what are the boundary points going to be? Exactly, the boundary is going to be this little square right here. All right, and are these points included right here? Well, yes, they are, because we are interested in values of x less than or equal to 5, which means that region is included. What about this region right here? Well, we are interested in values of y less than or equal to 5, which means that's included. Same with these two regions here. So all of the boundary points of this region are included in R1, so therefore this region right here is closed. All right, so far so good. All right, so next we're going to look at R2, which is we're looking at values of x and y, where x is between 3 and 5, not including the endpoints, and y is between 1 and 4. All right, so x is between 3 and 5, y is between 1 and 4. And since it does not include the endpoints, we draw a shaded dotted line there. All right, and this is our region in question there. So now the question is, does it include any of its boundary points? If we think about it here for a second, the boundaries are that one there, that one there, that one there, and that one there. So does this region here include any of its boundary points? The answer is no, because on all of the boundaries there, we have a dotted line there. Since it does not include any of its boundary points, the region in question is going to be open. All right, and now finally we're going to look at R3, which says x is between 1 and 2, do not included, and y is between 1 and 3. So x is between 1 and 2, y is between 1 and 3. So this is the region we end up getting here. And now we would like to determine whether this region is open or closed. All right, and now if we think about it for a second here, this boundary point is included. Right? So can it be open? Remember, for it to be open, it cannot include any of its boundary points. As soon as it includes one of its boundary points here, it can no longer be open. Now the question is, so this is not open. The question is, can it be closed? For it to be closed, remember, it should include all of its boundary points. And if we look at this portion here where x is equal to 2, that region of the boundary is not included. So this one is not open nor closed. All right, so it's neither open nor closed. So again, that can happen. So you could have a closed, open, or neither open nor closed. All right, so now that we know what it means for a region R to be closed, open, or neither, we're going to define what a global max and a global min of a function is. So let f of xy be a two-variable function, R be a region that we select that's from the domain of our function, and let's say a comma b is a point in our region R. We say our function f has a global maximum ab, and the global maximum of f of x comma y on R is the value f of ab, such that if the value of the function at a comma b is greater than or equal to the value of the function at point x of y for all points x comma y in R. Alright, so if f of a comma b is bigger than or equal to f of x comma y for any point x comma y in R, we say our function has a global maxima or maximum. Similarly, f of a b is a global minimum if f of a comma b is less than or equal to f of x comma y for all points x comma y in our region R. And finally, we say the global max and global minimum are called global extreme values. So the global extreme values of f of x comma y on R are global maximum or global minimum, all right, values of f in R. All right, any questions here so far? All right, wonderful. All right, so now that we're equipped with the definition of global max and global min, and we know what a closed and open set is, I'd like to talk about one final definition, and that is what is called the closed disk. All right, so closed here means, again, that it should include all its boundary points. And the notation we're going to use is going to be DAB. R is going to be a closed disk centered at AB with radius R. All right, so in other words, it's a set of all points on the xy plane whose distance from AB is less than or equal to R. So here's a picture I want you to keep in mind. Here's my point AB. The closed disk is going to be all the points here that are distance R, at most distance R away from our point A comma B. If I was to express this in set notation here, it would be all points x comma y, such that if I look at the distance, so if I look at x minus a squared plus y minus b squared, that entire thing inside a square root, that's the distance from xy to AB, we know that distance should be less than or equal to R. All right, we want it to be less than or equal to because we want to include the boundary points there as well, because we're looking for a closed disk. All right, so that might be something novel, something new we've not seen before, but if you have any questions, please let me know during office hours. But for now, the definition of closed disk allows us to define what we are going to refer to as a bounded region. All right, and so a bounded region, we say R, a region R is bounded if it can be completely contained in a closed disk. All right, so if we can find a closed disk in which we can completely include our region, then we call it bounded. All right, so again, let's get a feel for what a bounded region is. So let's look at the region R that is given by 0, 1 cross negative 4, 4. Again, this here is supposed to represent a rectangle, and let me introduce this notation here because we're gonna use this notation a lot moving forward. So when I say this here, what I mean by that is we're looking at all coordinates x comma y, where x lives in this interval 0, 1, and y lives in this interval negative 4 comma 4. And again, these boundary points here are included in this case here, right? So the interval notation. So when I write it in this form here, 0, 1 cross negative 4, 4, that means we're referring to a rectangle whose x value is between 0 and 1, endpoints included, and its y values are between negative 4 and 4, endpoints included again. All right, so let's go ahead and sketch this one here. So x we know is between 0 and 1, y is between negative 4 and 4. So it's right here. All right, so right there. Again, bear with me. Negative 4 and 4. So we're looking at this region here is our region R. So now the question is, can I create a disk big enough that includes all of these points here? Again, the answer should be yes, because, all right, so again, that's supposed to be a disk centered at 0, 0 of radius 5, right? And as we notice, this entire region is contained completely in that disk there. All right, so in this case here, we realize the region in question is bounded. All right, again, does not matter how big the disk is. You might say, hey, we didn't need to use that size disk. We can use a bigger size disk. It does not matter. As long as we can find some disk centered somewhere that the region is going to be completely contained in that disk, we're good. So you could have said, hey, I would like the disk to be centered at this point here, and picked up a bigger disk. That would have been okay too. All right, so for instance, you could have picked a disk, and again, it's this shine disk here. That would have been fine too, because all we need is this region here in question to be included in some closed disk centered at some point. All right, so you might think that is quite vague. You might even think that's always possible. So let's look at the following region. Now we are going to look at the region x is bigger than or equal to 2. All right, so if I look at that one there, this is my line, x is equal to 2. And when we're looking at bigger than 2, that means we're looking at all the region to the right of this here. All right, so it extends infinitely in the x direction, and it extends infinitely in the y direction, both cases here. So the question is, can we find a disk large enough that's going to contain all of these points here? And the answer is no, because no matter how big a disk we take, it's never going to contain everything in this region here. So I could start with something like this here, that disk, there's points outside. Could take another disk here, point's going to be outside. I could take even a bigger disk here. Again, there's going to be points out here and out here that are not contained in the disk. So no matter how large I take this disk here, it's not going to contain all of those points in question here. So this thing here is not bounded. All right, so now we know what it means for a region to be closed. We know what it means for a region to be bounded. And this is going to allow us to state the extreme value theorem for a function of two variables. All right? And the statement of extreme value theorem is the following. So if we're given a smooth function, all right, smooth function of two variables, all right, remember smooth means we can take as many derivatives of that function as we want to. Everything's nice. And let's say R is a closed and bounded region. All right, so we have a smooth function of two variables and we have a closed and bounded region. Then we can find points x1, y1 in our closed and bounded region so that f of x1 is the global max and f of x2, y2 is the global min. All right, so what this statement is saying is if we have a smooth function of two variable on a region that is closed and bounded, that function always obtains its global maximum and global minimum on that region there. All right, so I would like you to think about this in the context of a function of single variable. Remember, we needed our function to be smooth, nice enough, and we needed to have closed intervals, remember, because if we had open intervals, as we saw in our homework, we're not necessarily guaranteed to have a global max and global min of a function of one variable on an open interval. Similarly, for a function of two variables to obtain a global max and a global min, for us to guarantee that there's going to be a global max and a global min, the region we're working over better be closed and bounded. We are not saying if it is not closed and not bounded, then the function is not going to find its global max and global min. There are going to be examples where it's not closed, not bounded, but still our function of two variables is going to obtain a global max and a global min. What this statement is saying is if we want to guarantee that there's going to be a global max and a global min, the function better be smooth and the region in question better be closed and bounded. All right, so now that we have the statement for extreme value theorem, we are going to define the closed set method. Again, the idea is going to be same as a function of one variable. First one is find all the critical points of our function in question and find the values of our function at those critical points there. Step 2 is going to be we're going to find the maximum minimum values of our function on the boundary of our region, just like we checked the endpoints in a closed interval method. And finally, once we evaluate the function of our critical points, find the maximum and minimum value of our function on the boundary, we're going to look at the largest of these values here. That's going to be our global max. And the smallest of these values are going to be our global min. All right, so it might sound somewhat convoluted here, but what we're going to do is we are going to look at an example, and we're going to work slowly through this example in question. All right, so the example we're going to be looking at is we are going to look at a function which is x squared plus y squared minus 2x plus 2y plus 5, which again is a polynomial in two variables, so everything's going to be nice. And the region we're going to be looking at is a closed rectangle bounded by the lines y equals -2, y equals 2, x equals 0, and x equals 3. And if you look at this, it's going to be this region here in question. All right, so it's this region. So what we want to do is we want to find the global max and global min of our function on this region here. So the first question we'd like to ask ourselves is, are we always guaranteed to have a global max and global min for that function on this region here? And the answer is no. F is smooth, right? And our region R is closed because if you look at all the boundary points here, all the boundaries are included in our region because we have a solid line, not a dotted line. And if it's bounded, yes, I can find a disk big enough that's going to include all of these here and is bounded. All right, so if we have a smooth function and our region is closed and bounded, we are guaranteed to have a global max and a global min. And we're going to work through this step by step. So the first step is going to be find the critical points and evaluate our function at those critical points there. So if we want to find our critical points, first we need to find the partial derivatives of our function with respect to x, respect to y, set them equal to 0. So in this case, the partial derivative of my function with respect to x, all right, again, the derivative of x squared with respect to x is 2x. The derivative of y squared with respect to x, again, we're going to hold y as a constant. So in this case, we're going to get 0. Minus the derivative of 2x is 2. And the rest is going to be 0. And the partial derivative of the function with respect to y is going to be 2y plus 2. All right, so those are the partial derivatives of our function with respect to x and with respect to y. So now if we want to find the critical points, we are interested in points where the partial derivatives both vanish or one of the partial derivatives is not defined. All right, so the not defined portions are not going to be important in this case since we have polynomials, everything's going to be defined. So the critical points are going to be exactly the points where the partial derivative with respect to x and the partial derivative with respect to y vanish. So let's look at partial derivative with respect to x first. So let's go ahead and set fx equals 0. In that case, I get 2x minus 2 is equal to 0. And then we get x is equal to 1. And next, when we set partial derivative of f with respect to y is equal to 0, we're going to get 2y plus 2 is equal to 0, which means we get y is equal to -1. So what we can conclude from this here is, therefore, we have one critical point. So our function in question has one critical point, and the critical point is 1, -1 is a critical point of f. Alright, so we know that 1, -1 is a critical point, but remember, we are interested in this region R. We do not care for points that are outside this region R. So what we would like to do is go ahead and verify that this point 1, -1 is in fact in our region R. And if I look at this, my point 1, -1 is right there. That's my critical point. It is in region R. So we're going to go ahead and evaluate our function f at 1, -1. And when I do that, I get 1 squared, which is 1, plus -1 squared, which is 1, minus 2 minus 2 plus 5. So I get 2 minus 4 plus 5, which is equal to 3. All right, so we're going to underline the values that could be our global max and global min. All right, so again, what we did in this portion here is we found the critical points of our function, verified that the critical points of the function are indeed in that region. If it was not in the region, we would disregard the ones that were not in the region R and evaluate the function at the critical points that are in our region R. So that's step 1. All right, so step 2, what we're going to do is we are going to look at the boundary. We're going to look at the maximum and minimum function, the maximum and minimum value of our function along the boundary. And if you think about it, our boundary here is separated into 4 distinct pieces, right? So there's the bottom edge, there's the right edge, there's the top edge, and there's the left edge. So what we are going to do is, for right now, I'm going to concentrate on the bottom edge of the boundary. All right, so let's look at the bottom edge. Right, so if we're looking at the bottom edge of the boundary, is there an equation that describes the bottom edge? So is there anything special? The answer is yes. The y value of our function is fixed along the bottom edge. So in this case, our y is actually equal to -2. All right, so now remember, our function is x squared plus y squared minus 2x plus 2y plus 5. But when we're looking at the bottom edge, our y is equal to -2. So on the bottom edge, on the boundary, y is equal to -2, our function behaves, or our function becomes, right, it becomes, so again, sorry about the technical difficulty. So we're looking at, on the boundary y equals -2, our function here becomes f of x, but what happens to our y value? It becomes -2. All right, so in this case here, we're going to get x squared plus, what is our y? Well, it's -2 squared minus 2x plus 2 times -2 plus 5. So if we think about it for a second here, on the bottom edge, when y is equal to -2, our function becomes a function of a single variable, which I'm going to call g of x. And if I simplify this here, g of x is going to equal x squared minus 2x plus 5. All right, so that's the function here on this boundary here, but let's look at it. Can our function g of x take on any value for x? So the question is, can x be any number, or is there going to be a restriction on x? And if I look at it here, this is the edge I'm looking at right here. The smallest value of x I can take on is right here, and the largest value of x I can take on is right there. So in this case, an x, it belongs to the closed interval interval 0, 3. Right? So what that means now is that we have our function g of x, which is x squared minus 2x plus 5, and we know our function takes on x values only in this closed interval 0, 3. So we have a nice enough function, a polynomial, on a closed interval. Wouldn't it be nice if we had a method of finding the max and min of a single variable function on a closed interval? And this is exactly the closed interval method we discussed last class. So what we're going to do now is we're going to apply closed interval method here. So what we're going to do is we're going to apply closed interval method. Our function is g of x is equal to x squared minus 2x plus 5, and our x value is between 0 and 3. So what we're going to do first in the closed interval method again is find the critical points. So g prime of x is going to equal 2x minus 2. Set it equal to 0. So in that case, we're going to get x is equal to 1. So that's the critical point of my function here. Is that critical point in our interval 0, 3? And the answer is yes. So now, next we're going to go ahead and evaluate our function at 0. When I do that, I'm going to get 0 squared minus 2 times 0 plus 5, just 5. We're going to evaluate g at our critical point, which is 1. So I get 1 squared minus 2 times 1 plus 5, which is going to equal 4. And then g of 3 is going to be 3 squared minus 6, which is 3, plus 5, which is 8. So those are the candidates for our global max and global min on the region R here. So just to recap what we did here so far, what we said was we were going to concentrate on the bottom edge of this region here. And the bottom edge, remember, was given by y is equal to -2. So what we're going to do is we're going to take that, plug it into our function, and our function now becomes a function of a single variable right there. And it is going to be defined on a closed interval. So if we're trying to find a maximum and minimum of a function of a single variable on a closed interval, we can use the closed interval method, which says the global max and global min of our function can only be obtained either at the critical point or at the endpoints. So we're going to go ahead, find all the critical points in that region there, evaluate the function at the critical point and at the endpoint, and those are the candidates for the global max and global min of our function. Now what we're going to do is we will repeat this process for the remaining 3 boundaries. So repeat process for remaining 3 boundaries. So we're going to get 3 different sides boundaries. And rather than working through this here, what I'd like you to do is I'd like you to pause this video here and see what you get for y is equal to 2, for x is equal to 0, x is equal to 3, and a couple of seconds you're going to see the answer pop up on the screen here. But what I'd like you to do is I'd like you to pause this video here and see if you can repeat this process here for the remaining 3 boundaries. All right, so if you did it for the remaining three boundaries, so for the top boundary, which is y is equal to 2, your function becomes a single variable, a function x squared minus 2x plus 13 for x in 0, 3. So when you do that along the boundary, you get values 13, 12, and 16. Now, for the left boundary, remember your boundary is x equals 0. So now your function becomes a function of a single variable, but in this case it's going to be y. And remember, if you look at the region here, we're on this line here now, x is equal to 0, and our y takes on value between 2 and -2, and that's exactly what we have here. Again, we are going to have a polynomial on a closed interval, so the same process applies here. And you're going to do the same thing for the right edge, which is going to give you these three values here. All right, so all the numbers here that are underlined are double underlined here are the candidates for our global max and global min of our function of two variables. All right, so again, remember, it's always easy to forget, but we have another number here all the way in the distance, which was the value of the function at our critical point and at the boundaries there. So if you compare all of these numbers here, what is the maximum value you see? Well, the maximum value we see is 16 right here at, well, x is equal to 3. And do we know what the value of y is on that thing there? Remember, this was exactly the point, y is equal to 2. So we get x 3, 2. You might say, hey, am I getting 16 here? I see 16 here again showing up. But if you look at it for a second here, what is your x value? Is 3. What is your y value? It's 2. So it really is at this corner right here. And this corner, since it falls on both boundary points, we end up evaluating this twice. All right, now what about the minimum value? I see a bunch of numbers here. The smallest one I see is 3. So we know that the global min of our function is going to be 3 at point 1, negative 1. All right, so again, where it's evaluated is just based on the computation here. That's not of most important. The most important thing here is what the global max and global min of our function of two variables are. All right, so you'll get plenty of practice with these kind of questions on the homework. Again, please remember, if you have any questions, discuss amongst yourselves in the group, or you can swing by office hours on Zoom. All right, that's it for right now. I will post, I'll talk to you on the next video.